So last time I was talking about how we make a surface, and so you start with a bunch of voxels, just 3D voxels, and then you decide where the boundary between gray matter and white matter is. And so the idea is you've got this huge pile of cubes, and then you say that these guys are classified as white matter, and the ones outside of them are not. And you might wonder, like, so why do you go for the gray matter, white matter border? It's because that approaches itself a little less closely than the outer surface of the gray matter, because the outer surface of the gray matter is right up against itself, whereas the gray white matter border is a little bit further away from itself, and so it's less likely to get confused. But basically, you take that thing, which is a 3D data set. It just says white matter or not white matter, and then you turn it into a surface, and turn it into a surface by kind of finding all the neighbors, and so every vertex knows its neighbors, and so then you have this very lumpy surface. It's just the faces of these cubes, voxel cubes, that you identified as white matter. And so what we want to do now is that looks kind of jaggedy, and so let's refine it and do various things with it. So we could make a better estimate, like a subvoxel estimate of where the gray white matter surface is, or we could inflate the surface so we can sort of see all the different activity in different parts of it, or flatten it, or try to find the peel surface. So that would be the surface, this surface right here. So the gray white matter surface is something that like that, but we could also try to find the peel surface. That the pia is the outer layer of the cortex. So and then we could also do other things like try to align brains on the surface, and I'll talk about that on Wednesday. But today what I want to talk about is basically how we refine the surface. And most of the way these methods, so this the FreeSurfer software that me and Anders Dale mainly originally wrote back in the 90s, which is now heavily used. The way I'm going to describe it now is not the way that we thought it up. So the way I'm going to describe it is the more mathematically correct way of describing what we're doing. But that doesn't always happen. You might be educated properly in math, but often people who are educated properly in math might not necessarily know what a problem to work on is, and so development happens both ways. So the intuitive way that we came up with it, I'll just sort of go over that quickly. So how do you reduce curvature of that surface? So that surface is very, very jaggedy. So how do you reduce curvature? Well, it's very simple. If you just have, say you have, 3 neighbors of this guy. So here's 4 vertices, and here's a vector that goes to the neighbors, to the neighboring vertices. And that would form 3 triangular faces like that. And so how do you reduce curvature? It's very straightforward. You first calculate the surface normal. So here's the surface normal. There's various ways of doing that, but just find out the vector that's the sort of the average perpendicular to these faces, the surrounding faces. And then what you do is you just do a dot product between that normal So if you do a dot product, if that normal, so this guy is the normal, if that normal has a length of 1, because you normalized it, it's a normalized normal, then what you can do is just do a dot product, and that dot product will basically give you this vector, or the length of this vector. And what is that? That's kind of how curved it is. So if that length of that vector was 0, it would be just a flat plane. If it's concave, then that vector is going to have a positive number. If it's convex, that vector would have a negative number. The dot product between this vector going to the nearby vertex and the normal. So that's how you get rid of curvature. Just project onto the normal and then see if you get a positive or negative, and then move this guy to reduce that number. So that's a very intuitive way to think about it. What about reducing distortion? You have a same problem, so you could, how do you reduce distortion? So a similar thing can go on, but using like a different. So here's our 3 vertices again, or 4 vertices again. So what you can do now is basically so here's these vectors to the nearby vertices, to the neighboring vertices, and now get the normal again, but now do the perpendicular projection onto the normal. So if you do the perpendicular projection onto the normal, that's going to be, so here, find that guy. So if you find that guy, that's kind of just the other, that's the other leg of of this triangle here. And then if you essentially add up all the equivalent vectors, there's going to be an equivalent vector going to this guy and an equivalent vector going to this guy, and those guys will all be sort of perpendicular to that normal. That's going to, if you add those up, that's going to move you in the direction of less squishing. So we want to sort of get rid of, so that will, technical term is squishing. So, like what if the vertices look like this? That's kind of, this guy, there's the triangular faces like that, that's kind of squished. And so what would you do? Just go that way. So that's how we came up with the algorithm for refining the surface. You just, just fix the parts that are convex and concave. If you want to smooth it out, and just redistribute the vertices so that you reduce the distortion, and that will sort of, if you do those both at the same time, then you can do a nice refinement of the surface. So, but that's not kind of the mathematically proper way to describe it. And so when you eventually published the paper on FreeSurfer paper, it was sort of done the right way. And so what's the right way? So the right way is we have to define an error, and then sort of an error in smoothness, an error in squishiness, like how, badly distributed are the vertices, or sort of how, a non-uniform are the little faces. And then finally, we want to refine it against data. Are we in the right part of the gray matter? Are we at the gray-white matter border? So we define an error in those 3 things. And then we take the derivative of it. And the derivative of it tells us how to minimize it. And I'll make a sort of a spatial diagram of that. And so we'll end up with the same thing as we already came up with, but that's the proper way to describe it. And so here's the total error, and the total error is just a number, a single number. So single number j. So that's the total error. and that's going to equal this lambda is just a weight, like how it's going to equal some weight for the normal error, like how much should we pay attention to the normal error times the normal error. So here's the norm. So that's just, those are just two numbers multiplied by each other. And then there's going to be a tangential error. That's the one that's sort of the squishing error, where the mesh isn't, the vertices in the mesh aren't uniformly distributed, and so it's distorting these, the area of these original faces, and so then there'll be a tangential error number, and then finally there'll be image error. So then, and that'll have to do with where the vertex is relative to the gray-white matter image. So we already sort of used the image to generate the surface, but then we can go back to the image and say, that this vertex here, is this vertex sort of at an image voxel that is the right image voxel that we actually want. And so there'll be an image error here. So that's basically that's our error function before we sort of expand it. So error function that we want to minimize. So this is basically total, and it's across the entire brain, right? So this is total, total error across the entire brain. Just a number, single number. This one is, I put tangential first, so it doesn't matter. Okay, so this is scalar curve, fix by perpendicular move. And then this one is scalar squish. Is that what I wrote? Scalar squish. How much squishing is there? Just a single number that describes how much squishing is there. And this, fix by, parallel move. You move the vertex kind of parallel to the surface. And then this is, scalar image. So it's just a number saying how much total, and just, fix by move to target. So there, you say we should be at voxel value 110. And so, which way do you need to go to get to 110? Okay, so that's our overall error. So now what we need to do is write them out and say what each of the j's. How do you calculate the j's? So to calculate the scalar error. And so I'll start off with the normal one. So normal meaning perpendicular. So J, I leave enough space over here. So J normal. So at first equals 1/2. Now we're going to have something squared, and when we take the derivative of something squared, we'll get 2 times something. And so if we take half of it, it gets rid of that. So that's what the half is for. And then times the number of vertices there. So it's kind of, we're dividing by the number of vertices so that it's kind of, the number ends up being sort of error per vertex, average error per vertex. Okay, and then it's going to be summed over all of the centers. I'll make a drawing over here of what we're actually doing. So each vertex, that's each vertex center. But you remember that last picture that I erased about how you fix the curvature. It involves the relationship to the neighbors, and so we've got so it's a double sum. So it, for each center, sum across all the neighbors at that that are around a single center. So it's a double loop, like a loop within a loop. And then what are we summing that actually is the error? So the error is the normal vector, which is the normal vector at the center. And then dot producted with the vector that is the one that I drew that goes from the center vertex to one of the neighbors. And so what is that vector that goes from the center vertex? It's actually a vector subtraction of the vector that goes from the center of the coordinate system, and then subtract off the center vector also coming from the center of the coordinate system. So what does that look like over here? So if we've got our vertex here. So there's our center vertex, and then we're going to have a vertex here, and here, and here. Okay, so these are, and here's the face. Here's the actual sort of faces. And so let's take like one of these. So, and then we've got a normal. So let's put our normal. Let's put the first vectors in there. So if here's the 0 of the coordinate system, let's put it right there. So that's 0, 0, 0. So that's the center of the brain. And so here's a vector going to the center. So you can sort of think of the center as you can sort of think of it as as a point, but a point is a kind of a vector going from the center of the coordinate system. And then here's a neighbor. Here's the neighboring vector. So this guy is the. So what are those? So this is. This is the vector that goes from the center of the coordinate system to the neighboring vertices, and here's the vector that goes from the center of the coordinate system to the center vertex. And so if you subtract, so this subtraction is a little confusing. So if you start with the neighbor vector and then subtract off the center vector, that means reverse the center vector and stick it tip to tail. You'll come down to here and you'll get a vector. You'll get this vector here. And so that guy is neighbor vector minus center vector. So then we've got a normal. So here's a normal vector. And how do we get the? So that's the normal vector of the center point. So there's several ways to get it. You could get it by doing a bunch of cross products between these, neighboring vectors like this. So if you do a cross product between these two guys, that's going to find a vector that's perpendicular to both of those. Then if you do a cross product between these two guys, you'll find another vector that's perpendicular to this triangle, and then a third one. They'll all be slightly different from each other, and add them all up and normalize them, which means like divide by their amplitude. Then you'll get a length 1 vector. So length equals 1. A normalized normal vector. Normalized meaning its length is 1, and so it just points in a certain direction with length 1. So that's our center vector there, and so now let's finish the equation here. So then we're going to take that and square it. And so why do you square it? So the idea is that if and what does this mean here? So what this means here is do a dot product. So this is, dot product of those two vectors. And so what are those two vectors? Those two vectors were the normal vector here and the vector going to the neighboring vertex. And if you do a dot product of those, remember a dot product says, if they're very similar, the dot product's big. If they're at right angles to each other, it's 0. If they're similar but opposite directions, it's negative. So this guy is the normal that's approximately normal to all these guys. Won't be exactly normal to any of them, but it's kind of the average normal. When we do the dot product, if we do a dot product with a vector that is length 1, then it's just it corresponds to the projection onto that vector. So what that will do is that will just say let's find perpendicular to that normal vector, and then basically find this length. So the dot product is a scalar. So the dot product is just this is dot, the length of that guy, and so that number will, if it's positive, that means we're concave. And if it's negative, that means we're convex. So this dot product could be positive or negative. When we square it, we get a positive number, and so then we just have sort of the total amount of error, whether it's concave or convex. Now that sort of seems like a bad thing to do because we need to know which way to go. But once we take the derivative, we'll get back to a direction. So basically, this is just a single number across the entire surface that just says how convex or concave is it on average across the whole mess. Okay, so this guy is vect2 neighbor, and this guy is normalized normal. That normalized meaning length equals 1, normal meaning perpendicular to the surface. So then we just have, so that's a single number that just tells us how convex and concave are we, and we want to sort of flatten the surface out, and so we want to reduce that. So then the second thing is the tangential one. That's a little bit more complicated because the way it's written in the paper, it's 1 over 2 times the number of vertices again. But now we have something else, which is we need a coordinate system perpendicular to the normal. And so you could imagine we've got a coordinate system. I'll just draw it like this. So these are sort of coming out at you. So this is a coordinate system that's perpendicular to the normal. And so this one is called, T, like say the x coordinate of the center. So it's a unit vector that is perpendicular to the normal, and it sort of defines like the x direction. So this is Tx of the center, and this guy is Ty of the center. So how can you get those guys? So that's kind of like a little local coordinate system around our center vertex. And, this guy is going to be, everything's perpendicular, right? It's perpendicular to that guy, and this guy is also perpendicular to that guy. So one way of getting it is you can take the principal components of the surrounding cloud. So, what is the principal? So imagine, and there's only 3 that I drew here, but here's an example. So this guy just has 3, but here's another. You can have up to 6 vertices on this surface. Like, look at this vertex right here. That one has 1, 2, 3, 4, 5 neighbors. So you can have different numbers of neighbors. But if you think of those neighbors as a cloud of points, and then just take the principal components of it, solve the eigenvector problem, eigenvalue problem, and to see how, what is the best fitting ellipsoid that will fit over those surrounding points. What's going to happen? Well, the first 2 principal components will be these xy vectors, because that's the direction in which the cloud is most elongated if it's sort of a rumply but somewhat flat surface. And the third eigenvector, which will be perpendicular to the first 2, is the surface normal. So that's another way of calculating the surface normal. You can just basically do the principal components of the cloud of vertices. You think of the surrounding vertices as a cloud of points and fit an ellipsoid to it. That's what principal components, what an eigenvector problem will do. So that's one way of getting this kind of local coordinate system. And so then what do we do with that local coordinate system? We sort of project onto it. So it's the same kind of thing. So now we're summing over the centers. So for each center, sum across all the neighbors, the following thing. And so now it's a little more complicated because we've got sort of 2 components. So we have this x component, the x unit vector, this guy right here. So that guy's a vector, and we're essentially, instead of projecting this vertex onto the normal, we're projecting it onto the finding how much of its direction lies in the direction of this x-axis of our local coordinate system. And so it's the same thing here. So it's the same vector that goes between the center point and the neighboring point squared again, and then the same thing for the y component. And now, so what's actually going on here? And it's a dot product again. This is dot. So I'll make a little drawing of why this makes sense. It's just, you're sort of just decomposing this vector that's parallel to the normal into an x and a y component. Neighbor minus center, that whole thing squared. So if you look, say the surface was very squished. So we're looking down on it now. So just look down on the surface and say it was really squished, something like that. So, and say, let me put that up a little bit, and say here's our local coordinate system. So here's the tx, and so this is tx of the center point, and here's ty of the center point. So now let's project, say just project onto the x1. So here's the x1. And so what we want to do is project those three guys onto the x1. So here's the perpendicular projection, so it's that point. So that's the dot product. The length of that is the dot product of this guy onto the tx, and here's the dot product of this guy, that point. We'll put an x in at that point instead. So it's just the length. It's just that length, right? That's what the dot product is. It's a scalar. And then this guy over here, here's the projection, perpendicular projection on here. And so obviously this one is going to be really big. And so that's going to indicate there's a lot of x stretching going on. And then you do the same thing for the y. So it's just a way, this is just a way of sort of doing what we said originally, which was we just want to figure out which way to move the center point so that it sort of gets more equally distributed between, between these guys. And so if it's not equally distributed, you're going to get a big number, which means a big error, big scalar error over here. And it's squared so that if it doesn't matter if it's like, too far this way or too far that way, it comes out the same. It comes out to a positive number. Okay, so that's our tangential error, so that thing goes up into here. And so then finally, we have to calculate the image error. And so the image error is a slightly different thing. So the image error, so now we've got an image. So do we have one more color? Yeah, but it doesn't look that different. Well, let's try it. Okay, so now the problem is we've got some image data. And the image data is just a three-dimensional block. I'll just draw sort of two-dimensional voxels. So here's a bunch of two-dimensional voxels like this. And so this data point is sitting inside this voxel, okay? So so this guy is an image, and so what is that that image? Here, I'll do it over here. So what that image is some scalar value, not a vector value, at a particular R center. So that says, at this R center, or whatever voxel this R center is inside, that's what this means over here. There's going to be an image value, 110 or 112, whatever, something like that. And so that may not be the image value that we want the vertex to be at. And so then what we need to do is define an error for our image. And so this one, basically is just over the centers because it doesn't depend on the neighbors. So this is just over the centers. And it's just the difference between what our target is. So our target, so here's the scalar value of what we want the image to be. Or, sorry. And this could be different in different places. But say we want it to be sort of similar to gray matter. Then we could just put a number in here that's our gray matter target, and then we subtract off whatever the image value is where we currently are. So here's whatever voxel we're currently in, and square that. So what is that error? So say we want it to be at 110, and the current voxel that we were in was 100. Then we have to sort of go some direction to make that error less. And so that error could be either positive or negative, but we square it and we just get a positive number. Sum it up across all the centers, we get a whole total image error. So that's our set of definitions of our error. So now what do we do? So now what we do is we need to figure out how to reduce the error. And if you think of it in a very simple 1D case, if we have some function like this, and at a particular point in the function, we calculate the derivative. And derivative is just the slope. And so how would we say this is our error function? So this is, j going up in that direction, and this is some coordinate like x. So if we have a function like that, we've defined an error function, and if we can calculate the derivative at a point in that error function, then all we have to do is so this derivative is positive, that's a positive slope. So how do we minimize the error? We just take the negative of the derivative, and that tells us, just go that way. You want to minimize, if you're on a curve, you calculate the derivative and then take the negative of the derivative, and that tells you which way to go to, you want to go that way to minimize your error. So that's good for just one, but now we've got more than one dimension. And so what do you do when you've got more than one dimension? Then you've got sort of a little more complicated situation. So you have a situation where, let's just do it in 2 dimensions. So if you do it in 2 dimensions, you've got some surface like this. So here's some surface like that. And then we've got that surface is sort of sitting in a coordinate system, and the coordinate system, so here's, say here's the 0 of the coordinate system. So here's, here's the j direction. Okay, so it's error, is going up, and then you've got two different coordinates that you can change in order to reduce the error. So this guy was our neighbor. Leave that there. So you got 2 different coordinates that you can change in order to reduce your error. So here's one of them, and here's another one. So that's so say this is, x and y. So you can fiddle with x and y to reduce the error. So now what? Now the problem is, we've got this more complicated surface. And so what you do is you calculate the gradient, the directional derivative, as opposed to just that first derivative, which is just a slope. It was just a number. So the directional derivative, it's an actual vector quantity, and what is it? So it's normally written, I'll talk about this 2 lectures from now to define what it is, but it's normally written like that, sort of an upside down bold delta. And that's the gradient. And what is it? Well, the direction is the steepest uphill direction. And the length is how steep. How steep. So there's two things to that vector. And so what will that be? That will be a vector in some direction. Say it's that direction. So that's the gradient. So like what direction, in any kind of surface, you can just go out and look at the hillside. At some point in the hillside, there'll be a certain direction that's the steepest uphill direction. And then how steep it is indicates how, the arrow length will indicate, vector length will indicate how steep, what's the steepness of that. And so that's the gradient. And so what is gradient descent? Well, how do we want to reduce the error? We just go in the opposite direction. So if you just take the negative of the gradient, then that will tell us how to go downhill in the error function. And so that's all we need to do to figure out how to reduce our total error, which consists of, normal error, tangential error, image error, and possibly some other, other errors. So let's start off with, so basically what we want to do is we take the negative of the partial derivative of the error. So why is it a partial derivative of the error? With respect to this vector quantity, which is where the center vertex is, because that's how we're going to fix the error. We're just going to fix the error by moving the center vertex in some direction. But now we need to know a 3D direction that we need to move that vertex in. So it's a partial derivative because it's only dependent on the center point. So we're holding everything else constant. So that means that like all these surrounding vertices, those are constant. The normal, that's constant. We're not changing the normal. The only thing, it's a partial derivative because we can only fix this by moving the XYZ position of the center point. That's what the meaning of this thing is. So it means let's, find out, what is the directional derivative with respect to moving just the center point while leaving the surrounding points fixed and the normal fixed and the local coordinate system fixed. And basically take the negative of that, because that means we're doing gradient descent, because we want to reduce this error. And so what is that equal to? So let's do the image one first, because that's a little bit easier. So it's going to be that number up there, the strength of the image error, so we can have a knob that adjusts, like how important should the tangential error be? How important should the image error be? How important should if the image data is very noisy, then you would need to turn the image error down a little bit and allow the tangential error and the normal error to control things. So when we take the derivative of that, what we get is, so we got to take the derivative of this thing. So how do we do that? Well, it's squared, so it's going to be like the derivative of, x squared, equals 2x. So it's going to be 2, and that's going to be canceled out by this 1/2 here. But then we've got to sort of apply the chain rule. So the end result is going to be the whole function up there. So this target center minus whatever the voxel that we're currently in. It's going to be that number, but then we've got to take the derivative of this guy, but we're in a multi-dimensional setting, so that's going to be the derivative of this guy. It's got a negative there, so it's going to be the negative gradient of that function. So what does that mean? So say we're, let's just make a little drawing here. So here's our voxels, and say the gray matter is pretty bright. So here's the gray matter, and say here's say this is the CSF out here. It's dark. So this is gray matter. So if we're at a particular point someplace on our surface, how do we sort of figure out which way to go to fix things? And what is the gradient? The gradient is going to say which is the direction in which the image value is changing the most strongly, and what would that direction be? And that direction would be like that direction. So that's the direction in which the image is getting brightest the most. And how would you figure that out? How do you sort of calculate a gradient? We'll talk about it in 2 days, but basically you just go out a little bit in each direction and figure out which direction, and just take the weighted sum of all those little tests in all the x, y, z directions to figure out which is the one that's changing the most rapidly. So if you go out in the x and it's changing really rapidly, you go out in the y changing a little less rapidly, then your gradient will be somewhere between x and y, maybe more toward x if x was changing more rapidly. So this number right here will say, will essentially tell us which direction to go, because this thing is a vector. So this guy is a vector. So that one tells us which way to go. This guy's a scalar. This tells us like how far off are you. So once we've taken the derivative conveniently of this thing, we end up with something that has a direction in it again. It says, it tells us which way should we move this vertex in order to reduce its image error, essentially to make it, which way should we move it so that we'll get into a voxel that's more similar to our target. So that's how you reduce image error. You take the gradient of the T1 data. So this is like T1 weighted data. So if you take the gradient of that, that will essentially tell you which way to go if you're trying to make your surface more like a particular value of a voxel. Okay, so that was the easy one, sort of reasonably easy one. So now we got to take the derivative of the normal one. So we're going to add on another vector, and this other vector is our normal weight. Like how much are we saying that being having low curvature is important? That just weights that, and we can adjust that as we need be. And this one we have to sum over all the neighbors, because this one is only defined across the neighbors. And so what are we summing? So we're summing something that looks pretty much just like what we saw before, just slightly different. So it's basically a sort of this dot product between this neighbor minus center. That's the vector going to the neighbor. But then we're multiplied by the negative of the center vector. Negative just means reverse, head and tail. So how do we get that? So how on earth is that the derivative of this guy? So one way of thinking of it is, so what did we have up there before we? So we had the n center dot producted with the r neighbor minus r center. And so if we remember that we're doing a partial derivative, so that means that we're holding everything constant except the center, then what we have is constant 1 times constant 2, because the neighboring vertex is constant, minus variable. And so, if you distribute that, then you have, constant 1 times constant 2 minus constant 1 times variable. And when we take the derivative of a constant, it's 0. When we take the derivative of this guy, we just get constant 1. So constant 1 is this guy up here. So, sorry, no. Not that guy. It's the normal. Okay, yes, it's actually that guy. Okay, so that's why this guy is appears here. So let's look at what this equation says. It just says, so it's the chain rule again. So it's the whole mess times the derivative of the mess, and the derivative of the mess turns out to just be this constant. But now we have something that will implement exactly what we just intuitively implemented at the beginning. So what is this thing? This is a scalar. This just says, this is a signed scalar, which tells us, which are we convex or concave, and how convex or concave we are. So this is, how convex, which would be negative, or concave, which would be positive. So how convex, concave, and then this thing is just the negative of the surface normal. So the surface normal sticking out, so it's just the negative of the surface normal. So this guy is, which way to go. And if you work out there's a negative here and a second negative here, you'll see that if you figure out how much are you convex or concave, and then for this vertex it will tell us to either move in or out to fix either convex or concave. So then last but not least we have to add on the fixing the squishing, and fixing the squishing is sort of similar. So it's across all the neighbors, and now weighted by our tangential weight. So do we want to make the surface very stiff and not very stretchable, or do we want to allow it to stretch a little bit? And then that's going to be multiplied by our dot product of the vector going to the neighbors minus the vector going to the that's this guy again, except now we're doing the dot product onto this xy coordinate system, and it will this guy will be multiplied by the negative of that constant local coordinate system vector, and then plus, and the squared goes away and gets canceled out by the two over here, and then the same thing for the y, this y local coordinate system vector, and then we're doing a dot product onto the neighbor minus the center vector, dot product on that guy, and then this vector, the ty center vector, will tell us the direction that we're going. So, and we'll make one more. Okay, there we go. So basically all that does is that will end up sort of moving us, and this is a vector sum of these guys. So this guy says how far to go in or out perpendicular to the surface. This one says, this one says what direction to go, which is an arbitrary direction, in order to make our vertex get into a voxel that's more similar to the target image that we want. This one says, what direction do we need to go perpendicular to the surface to reduce the curvature? And this one says, what direction do we need to go parallel to the surface in both the x and the y direction in order to reduce our squishing? And so there you have it. So that's how you can refine the surface. And you can do all different things with this. So you could try to refine the surface. So we start off with this very blocky surface, but what we could do is, end up, so if we have a surface that's just the surfaces, our initial surface is just going over, say it's trying to follow the gray matter, but it's just going like this, something like that. So that's not a very good estimate of the gray matter. And so if we want to make a subvoxel estimate of the gray matter, we run this whole thing with our original data that we made the blocky surface from in there. And then what that will do is that will, like in this case, this guy is very concave. And so what direction is this guy going to go? It's going to have to go out there. And this guy's, also concave. It's going to have to go out here. This guy is flat, so that guy won't move initially, but it might be moved by some of these other terms that are trying to redistribute the vertices around to make them to retain their original area, basically. And so what will happen is that you'll end up with this subvoxel estimate of where the surface is, something like that. So this is, voxel, better sub-estimate of, surface. Now, whereas our original data will be coarse. It will just say like white matter, white matter, white matter, white matter. But our new surface will be more accurate. And so that's how we get sort of a nice refined surface. And it can be so accurate that you can do something like calculate the cortical thickness, which is just a couple voxels thick. So it's a couple voxels, meaning if you just classified the voxels, you'd end up with very jaggy surfaces. But if you refine them, then you can actually calculate these subvoxel differences in cortical thickness. And so that's how FreeSurfer works, how part of FreeSurfer works. And what I'll talk about next time is we could add some more error terms. Like we could try to align a brain with another brain while still doing these other things, sort of keeping the surface vertices evenly distributed, not messing up the normal. So it's possible to add more error terms to this and take the derivative of them, the directional derivative, which will tell you which direction you need to move the vertex in order to fix it. And when you think about this, to finish up, this is like an incredibly brain-dead method. Now, it looks like a big mess, but it's really incredibly brain-dead. And why is it? It only looks at the neighbors. It pays no attention to anything else. So it just basically says, I'm just going to figure out how to move to, fix my image data and fix myself relative to my neighbors with tangential and fix myself relative to my neighbors with, with perpendicular, with normal. And I'm going to pretend like all the other guys are stationary. So, and then just go to each vertex, each time pretending that everybody else is stationary, and then go through the whole surface, and then figure out which way to move, then move the surface all at once, a little bit, and then do the same thing again and again. Now, you could do more intelligent kind of surface deformation if you tried to preserve something like more than just distances to the neighbors. What if you tried to preserve distances that went out sort of like 10 vertices or 100 vertices? Like preserve the shape of something. This doesn't really know anything about shape. All it knows is I'm just going to try to fix my vertex and screw everybody else. So it's possible to do that and use more complicated error functions that actually will look at larger scale things. Those are a lot more computationally inefficient. So this is extremely fast because it only has to look at the neighbors. But what are some of the problems that can occur? Well, what if what if your mesh looks like this? You've got some triangles that are all squished over here. And then over here, they start to get really big. Something like that. Now say you're in the squished part over here. You're a vertex in the squished part. Say you're right here. Now, which way should you go? No good way, right? So you just have to leave it up to this guy to figure out, oh, I should go that way to get a little unsquishing. So you can see, if you had some other measure that said, oh, I can see that there's a bunch of squishing going on in this part, and there's not much squishing going on in this part, I could use that information. But in order to calculate that, I'd have to go out to 5 or 10 neighbors, neighbors of neighbors of neighbors of neighbors. And that will greatly increase my computational load. So this is, it's the most basic brain dead way you could do it. Just pay no attention to anything beyond your local neighbors. So it looks kind of hard, but like I said, if you just start with the initial intuition, how do you fix curvature? Just, make it flatter. How do you fix, squish? Just go the other way to make it unsquished. How do you fix image? Just take the gradient and figure out which way we need to go in order to get inside our proper voxel. Okay, so that was a big load. Any questions about this? So this is equation 9 in our well-cited paper, which was unfortunately incorrect in the paper. So this is, it's been cited thousands and thousands of times, but this is corrected equation 9. So sorry about that. It's correct in the software, but it was incorrect in the paper describing the software. Okay, this is in Dale, Fischel, and Sereno, 1999. Okay, so any questions about FreeSurfer or gradient descent? Sort of the negative of the directional derivative tells us which way to go in order to fix our error, to make our error less. So this is the proper way to describe it. We define what the error is, and then we take the derivative and take the negative of it to figure out what direction to move this vertex. So the final thing that I didn't put in here, so there's going to be our final answer, and our final answer is going to be, well, we need to move a little bit that way. So that's our final answer. That's this thing here. So it's going to be a tiny movement of that vertex in order to reduce all these errors simultaneously. Okay. Questions out there? All good. Okay. Sorry about the late start, but I think we got a clear recording this time.